This video is intended for those who were not able to attend the consultation time during the synchronous period for this afternoon. I believe that's due to power outage. Anyway, I hope that this video material will help you in terms of how to calculate momentum and collision. This is very simple since we don't have time anymore. We're just giving you the basic and mimic how I solve the problem, okay? And please bear with me. I am not a blogger. I'm just doing this to help others who can learn through this video, okay? So again, if you want the things, you may refer to our Canvas page. And of course, what I'm going to discuss here is what I had listed also in our Canvas page, a portion only. Okay, so we're going to talk about the target is for you to be able to solve problems related to collision. Specifically, we're done with momentum. Now, you had learned this last time. The things that we were able to tackle, by the way, are the following: conservation of energy, momentum, impulse, conservation of momentum, 1D collisions, 2D collisions, and the center of mass. We are going to focus on the conservation of momentums, specifically on the calculations part. Okay? So, remember, in an isolated and closed system, the total momentum of the system remains constant in time. A little definition of terms here. When we say isolated system, no external forces, and closed system means no mass enters or leaves the system. So this is conservation of momentum. The linear momentum of each colliding body may change, but the total momentum of the system cannot change. And with this, we have the two types of collisions. So momentum is conserved in all collisions. There are two types. We have the inelastic collisions. Example, rubber ball and hard ball. Here, the kinetic energy is conserved. I am sometimes also confused on which one is conserved or which one is not. This is just a help for you. Okay. How will I know that kinetic energy is not conserved? What collision am I referring to? I hope this will be your guide. I usually use this one, this technique. Inelastic, not conserved. Because in the word elastic, there is no N, so kinetic energy are conserved. Well, I hope that helps. Anyway, so in elastic collisions, kinetic energy is conserved, and in perfectly inelastic collisions occur when objects stick together. Can you think of a real-world situation wherein you encountered a perfectly inelastic? Think of that. Next, elastic collisions. Example, the billiard ball. So are you familiar if you're playing? Both momentum here in the elastic collisions, that both momentum and kinetic energy are conserved. So in actual collisions, most of them fall between elastic and perfectly inelastic collisions. Another representation is using this image. Three types of collision: perfectly inelastic, and elastic. As you get to see here, As long as it stick together, that is inelastic. Okay? Perfectly inelastic. And somewhat bouncy, that is inelastic. And elastic collisions, these collisions are perfectly bouncy. And of course, I will be giving you some real world examples on that. Just a quick one. But again, my target is to present to you the calculations. Real world applications, maybe you were able to encounter Newton's cradle, this one. Okay, did you observe that the moment you raise one ball and release it, what happens to the other one, especially on the last part? Okay, so that's elastic collision. Take a look at the inelastic collision, the bumping of cars, colliding of cars. So the collision of billiard balls is nearly elastic because the kinetic energy is conserved before and after collision. Now, remember collision time when we discussed this in conservation of, impulse momentum theorem. The collision time affects the amount of force that an object experiences during collision. So the greater the time over which the collision occurs, meaning to say increasing time, the smaller the force acting on an object. Thus, to maximize the force experienced by an object during a collision time must be decreased. Likewise, to minimize the force, the collision time must be increased. So there are several real world applications of these phenomena. The airbags in automobiles increase the collapse time and minimize the effect of force on objects during a collision. So airbag accomplishes this by uh, extending the time required to stop the momentum of the passenger and the driver. Okay? So here is also an example of inelastic collision. Let me clear that. So what happened to the object, the red object, and the green one? Okay, so it's stuck, right? It's stuck. Now, um, let's review the equations for elastic. I'm sorry. For elastic, if you can recall, um, when the two objects collide, what happens after collision? They separate apart. So which means to say there is a before velocity and then after velocity. With regards to the mass, it, it does not change, right? So if it is elastic, we have M1 V1 plus M2 V2 is equal to M1 V1 prime. That prime apostrophe looks like an apostrophe, indicates that after collision, okay, then we have plus M2 V2 prime velocity, second velocity of the mass, of the second mass, okay, after collision. So please remember this equation that represents elastic collision. Now, in inelastic, since two objects stuck together, therefore they move in the same speed or velocity. Then we have their M1 V1 plus M2 V2 is equal to M1 plus M2, add them together, and the velocity final. Okay, so we will be using these two equations for the sample problems. Again, I have only two sample problems. One for elastic and the other one is for inelastic collision. Okay, let's have sample problem number one. Tom and his twin brother Tim have a combined mass of 200 kilograms, and are zooming along a 100 kilogram amusement park bumper car at 10 meters per second. They bump Melinda's car, which is sitting still. Melinda has a mass of 25 kilograms. After the elastic collision, the twins continue ahead with a speed of 4.12 meter per second. How fast is Melinda's car bumped across the floor? Okay, so let's draw. Physics can be best interpreted if it is illustrated, or you can understand it better if there's illustration. But I don't have such skill. Let's see if you will understand, no, my drawing skill. You have here the bumper. Let's assume that this is the bumper car, and there are two people, okay, riding on the car. This becomes our mass one. It's the object and the two brothers or the twins. Okay, then they are moving at a speed of 10 meter per second. Then on the other hand, Melinda is on in her bumper car and sitting still. Okay, that's Melinda. With the mass of, that's mass 2, Melinda's mass and the bumper car. So the velocity here is 0, right? Now, after collision, what happened? Okay, so Melinda, oops, why did I draw about Melinda? Sige na lang. Okay, Melinda, 0 meter per second. Riding on the bump car, still with the same mass, that's Melinda's mass. Okay, they bump, and meaning to say this has its own speed. Here, the two or the twins, okay, that it both carrying the same mass, okay, and it's also moving. As you get to see, basing from the equation, the twins continue ahead with 4.12 meter per second. Okay, that's the illustration. The next is, what's the velocity of Melinda? So given in the problem, we have mass 1 is 200 kilogram plus 100 kilogram. That includes the bumper car, that is 300 kilograms. Okay, then we have the speed of that, which is 10.0 meter per second. Mass 2, submass 2, that is Melinda and the bumper, we have 25 kilograms. And then the bumper car is 100 kilogram. That gives us 125 kilogram. The initial velocity of Melinda is 0 since it is sitting still. Okay, then there's another one, twins continue. This becomes V1 prime because this happened after collision. Its speed is 4.12 meter per second. So we are asked for V2 prime, Melinda's speed after collision. Our solution here is, since this did not, the situation did not, the two objects did not stick together, so we have elastic. M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime. So we substitute the value. We have 200, 300 kilogram times, well, prior to that, I would rather derive the equations first. Allow me to derive the equations, okay? So from that, we need to calculate this. So we transpose this on the other equation. You're familiar with this in your algebra. So M1 V1 plus M2 V2, the moment we transpose this part, this variable, it changes in its sign. We change it to M1 V1 prime equals to M2 V2 prime. It's not yet done. We need only the V2 prime, so we divide both sides by M2. Cancel, cancel. So V2 prime is M1 V1, that is 300 kilogram times the V1, that is 10 meter per second, plus M2 V2, our M2 V2 is 0, with, and then minus M, that is 125, no, sorry, that is 300 times V1 prime is 412 meter per second, divided by M2. That's M2. Okay? So, please calculate this in your calculator. You may use your calculator. Pause for a while and do the calculations. And after which, if you were able to get 14.1 meter per second, then you're in the right track. That is correct. Okay? So that's a sample problem for elastic collision. I hope that you get to practice this, okay, and do it on your own. If you want a sample practice problem, just PM Miss Michelle or message me via Canvas inbox. Next, we proceed to the second problem. Okay, the second problem. Here, sometimes the curiosity factor at the scene of a car accident is so great that it actually produces secondary accidents as a result, while people watch to see what it is going on. So, obras ang mga maniningad, right? So, if ever, no, we pass by scene of car accident, there are cases that we slow down and then we try to check and we even judge, right? Sino may sala. Anyway, with regards to this scene scenario, so the sports car slowed down at 13.0 meter per second. Okay? Then the truck behind him continues traveling 25 meter per second. And with that, they lock bumpers after a rear end collision. Okay? So let's have the car accident. So let's have the sports car. The mass, it has a mass, and that is 800 kilogram. The car is moving very slow, and the velocity is 13.0 meter per second. Here comes a truck, right? The truck is moving at 25 approaching the car 25 meter per second, that's V2, mass 2, and that is 1,200 kilogram. Okay, that's V2. After collision, what happens after collision? So we have the scenario that the truck got stuck also with, pardon with my illustration, with the sports car. Okay, so we have here the mass of the sports car, mass of the truck, and the question is, what velocity will the two move? Okay, what will be the velocity? Now, given in the problem, so we have mass 1 is equal to 800 kilograms. V1 is 13.0 meter per second. Mass 2 is 1,200 kilogram. Okay, with the velocity 2 of 25 meter per second. And then we have, that's it. Our ask is the final and solution, therefore, it's stuck together. This is perfectly inelastic. Our equation is M1V1 plus M2V2 is equal to M1 plus M2V final. With that equation, we will manipulate the equation and derive the solution for DF. We divide both sides by M1 plus M2, M1 plus M2. We cross out because that is equal to 1. We are left with VF. VF is M1 V1 plus M2 V2 over M1 plus M2. Our M1 V1 is 800 kilogram times 13.0 meter per second plus M2 is 1,200 with the velocity of, pardon me if you cannot anymore see it clearly, we divide it with M1, that is 800 plus 1,200. Okay, that's in kilogram. This is in kilogram meter per second. So 800 times 13, 1,200 times 25 divided by 2,000. What is your answer? Please pause for a while and check your answer. Calculate it in your calculator. Okay? So, therefore, what do we have here? The correct answer is, if you're able to get this, then again, you know how to manipulate your calculator. 20.2, that's the speed of the two. Okay? That's the speed of the sports car and the truck. Okay? So 9G, try to go over the video and then please work on this.